and also from the population statuses of living mammals. And those data sets are really valuable and obviously essential for, well, if you wanted to do anything about preserving the existing diversity into the future. But they are at the same time limited, if I may say so, in both the temporal scope. So what happened in the last 500 years may not be representative of what happens in the history of mammals in general, and also in the geographic scope, in that most of the extinctions, well, most of the recorded extinctions of vertebrates in the last 500 years took place on islands. So if we want to know, for example, the extinctions on continents or extinctions before modifications of environments by humans and hunting pressure, and also extinctions above the level of species, which is exactly what I'm going to talk about today, then the fossil record is really the key to understanding the dynamics of extinctions. Okay. So when I talk to people about the ongoing biodiversity crisis, I often get a response like, well, so extinctions happened all the time in the fossil record. Why should we be concerned about it? And we should be concerned about it because, well, aside from the fact that we care about these animals, because what's happening today is really quite abnormal in the Cenozoic history of mammals. This is, let's see. Oh. Looks like, no. It's like a slide just disappeared, but okay. I had a slide which may magically show up later, but of a figure showing the modern extinction rates. Let me just quickly find it. Okay, well, I don't know, like but the point I wanted to make is that in the last 500 years, 78 species of mammals became extinct in the wild, which is a tiny fraction of about 5,000 to 6,000 existing species of mammals. But if you think about the rate of extinction, that is actually surpasses the extinction rates estimated for most of the big 5 mass extinctions in the fossil record. Anyway, we get fascinated by large mammals, especially the giant ones from the past. And this is a picture from a vertebrate paleontology lab that I taught a few years ago. And here's a cranium of Indricothea from the Oligocene of Asia. This is the largest known land mammal in the history. And as you can see, people get really excited about these big animals. But what about small mammals? And sometimes students ask me if all mammals were big in the past, and that's obviously not the case. It's just that there used to be a lot of big mammals, and they are mostly gone. So I want to rewind the clock a little bit and start in the late Pleistocene, at the end of the Ice Age. You may have seen something like this. This is a mural in the Yale Peabody Museum in Connecticut, depicting scenery somewhere in North America at the end of the Ice Age. The landscape is teeming with big animals, things like the mastodon, that's Bison antiquus with huge horns. There was a giant sloth, and let's not forget the glyptodon, which is like a giant armadillo relative. And even things like beavers. This is extinct Pleistocene giant beaver called Castiroides, were huge. It may look small compared to elephants, but these giant beavers were probably about my size, well, weight-wise, maybe not length-wise. But, small mammals are nowhere to be seen, maybe hiding under these rocks. And what's really striking about the end Pleistocene extinction event is that, well, aside from the magnitude of it, most of the extinctions were those of large mammals weighing 10 kilograms or more, and I say that's large because most mammals weigh a lot less than 10 kilograms. These figures are showing the proportions of species that survived versus that didn't survive the Pleistocene-Holocene transition. So the ones in black are the victims of the late Pleistocene extinction event. And as you can see, basically we got rid of the tail end of the body weight spectrum. Just as an aside, one of the great mysteries is why the megafauna in Africa did relatively well compared to in other continents. And people often talk about how large mammals there evolved with humans, and so somehow things like elephants and antelopes had been more adapted to exploitative pressures from humans. I'm not entirely convinced by that, but there's something weird and interesting about Africa. That's the body size biased pattern of extinctions at the intercontinental scale. We can talk about things at the more local scale, right in our backyard in the East Bay. I worked on a project for a few years identifying fossil specimens from the town of Pacheco, which is just about half an hour of drive from here. From there we've got things like, well, obligatory mammoth, giant camels, horses, and at least a couple different species of giant sloth. There's also giant sloth from the downtown Berkeley bird station when they were excavating. And needless to say, all of these animals are gone. Okay, so what about small mammals? And I know most of the mammalogists in this room study small mammals. So Ron Wolf, who I think he just recently retired from University of Florida, but he was a graduate student here back in the 60s, and he did a dissertation looking at late Pleistocene small mammals from the East Bay area. He collected thousands of fossil bones by screen washing bulk sediment samples collected from basically road cuts along the Southern Pacific Railway in and around the town of Rodeo up there. And he identified a bunch of small mammals, I think 16, 17 species. He could identify all of these small mammals as living species. Not only are they living species, but we still have these exact same species in this area today. If you go to the Berkeley Hills, or I think this is a picture from snow, but gophers and voles and bunnies hopping around. And here's another vertebrate assemblage from the town of Pacheco. Based on a single radiocarbon date we have, it may be about 400 years old. It's the same, basically the same housing lot as where these big mammals are found, but these bones come from different stratigraphic layers, so they are not the same locality. But anyway, 400 years old assemblage. Well, this is showing the minimum number of individuals represented by the fossil bones in the collection we have downstairs. And there's really nothing that's hugely surprising about the relative abundance of these small mammals, with the exception for, well, we have somewhat underrepresented diurnal mammals like ground squirrels, because we have reasons to believe that this bone assemblage is largely derived from owl pellets. But otherwise, nothing really jumps out. And all of this is not to say that nothing has changed with small mammals since the late Pleistocene. For example, we have a couple species of voles from Pacheco that are no longer in the Bay Area. Chipmunk, we don't really have chipmunk in the East Bay Area today. So clearly these small mammals have shifted their ranges in significant ways at pretty fine time scale. But what I wanted to highlight here is that as far as extinction is concerned, we don't have good reason to suspect that small mammals as a whole any more vulnerable to extinction pressures compared to large mammals. So, okay, moving on to living mammals and their extinction risk. This is showing the proportions of threatened species in mammalian orders, and threatened is basically the threat status is evaluated by the International Union for Conservation of Nature. What I wanted to point out here is that those mammalian orders that have large-bodied species like primates, artiodactyls, carnivorans, and perissodactyls tend to be disproportionately threatened today. We can also look at the geographic pattern of body size and extinction risk. This is showing that in places where a fair number of large mammals survived the late Pleistocene extinction event, by that I mean like Africa, well, sub-Saharan Africa and parts of Asia, large body size is highly correlated with elevated extinction risk today. Oh, this is the figure I was looking for. Okay. Just jumped. Yes. Anyway, just to recap, the magnitude of extinctions for mammals in the last 500 years is pretty small, but the rate is abnormally high. And if we continue to lose mammals at the same rate, we will get to the magnitude of extinctions observed in the past mass extinction events in perhaps a few hundred years, if nothing is done. And so the body size bias pattern of extinctions and extinction risk are usually attributed to one or more of three major factors. So one is size biased exploitation by humans, so people going after big animals. Secondly, the low population size and abundance of large mammals. And also life history traits, which are strongly correlated with body size. So, for example, population density goes down dramatically as you scale up the body weight spectrum in mammals. And so in a few minutes I'll be talking about what I did, but I looked at durations of extinct mammalian genera in North America, partly because fossil species are difficult to compare with living species, but also from a macroevolutionary point of interest. I was interested in whether the pattern of extinction was preserved across different levels of phylogeny. What I want to bring attention to is that, well, so sometimes I come across these extreme views that genera are entirely artificial constructs of taxonomists, but really the correlation between body weight and things like population density, you can clearly see that at the genus level as well, which is really not surprising since closely related species within a genus tend to have similar body weights and similar ecological properties. And the same thing with generation time. Here I'm showing interbirth interval length, which is the number of days between successive births given by a female. Large mammals reproduce a lot more slowly than small ones, so in times of environmental change, large mammals may have harder time catching up with changes and therefore may become more vulnerable. So the basic question I'm trying to address here is whether large mammalian genera have higher probabilities of extinction compared to small mammals. That's really a simple question. And it turns out to be pretty complicated to work out with real data. But we might hypothesize that because of these factors that I just mentioned, large mammals may have higher probabilities of extinction and shorter durations in the fossil record, persisting for fewer millions of years. And several studies have looked into this problem and often came to apparently well, inconsistent conclusions. And what I want to point out here is that the answer to the question depends a lot on well, the geographic scale of inquiry, the time scale, the range of body size that's being investigated, and so on. So here's a study by Larry Flynn looking at Miocene mammals from northern Pakistan. He found that large mammals have much longer durations than small mammals. Now, of course, this is a relatively small geographic area, so we are probably talking about a lot of extirpations rather than true global extinctions. Liao and her colleagues looked at the Neogene fossil record of Europe, and they found that small mammals had significantly longer durations than large mammals. And the most recent study expanded the data set of Liao et al. And included parts of Africa and so on, but focusing on basically large mammals only, above, I guess, the body weight of a kilogram or so. Raya and his colleagues found no significant difference in durations between large and small mammals. Carnivorans have attracted a lot of attention, and dogs are particularly interesting in this regard, because if you look at the fossil record of North American dogs, the earliest ones, this is called Hesperocyon from the late Eocene to Oligocene of North America, were really small animals, I'd say about the size of skunks. This artist's reconstruction, well, these look suspiciously like meerkats, but we don't know about the bipedal stance and so on, but small dogs. And by the time we get to the late Miocene, we have giant canids like this Epicyon. So there's a strong trend of body size increase within the dog family in North America. And Van Valkenburg and her colleagues compared the durations of small versus large dogs in the fossil record and found that large dogs, which tend to be known from more recent part of the fossil record, had significantly shorter durations than small ones. In this case, the interpretation of this data is a little bit difficult because there's also a trend toward increased carnivory within the dog family at the same time when these animals are getting bigger. So it's not entirely clear whether it was the body size itself or a change in the diet of these animals that have something to do with apparently elevated extinction risk for large canids. Someone else looked at carnivorans in general from North America and Europe, and she found, well, no difference in small versus large carnivorans from the Miocene. So basically, all these conclusions are, well, all over the place, depending on what people have looked at, what method people used. And going back to this question, what I did was to use the generalized least squares regression method to take into account the possible, although not confirmed, phylogenetic covariance in the regression residual errors. We know that these data points, which represent different genera, are biologically not independent. And I also estimated the amount of phylogenetic signal in the dataset we have. And I tried to include as many extinct mammals from smallest ones, shrew-sized animals, to the largest mammals, I think, a rhino. I didn't include elephants because estimating body weight of extinct elephants is a little bit tricky. And I focused on the North American fossil record because we have reasonable probabilistic hypotheses for the North American fossil genera. They are not as available in Europe, so I got the fossil occurrence data from the MAP and FONMAP databases. These are publicly accessible databases of fossils from the Miocene and Miocene to Pliocene and Pleistocene. And this map is just showing the distribution of fossil occurrences in North America. I should say that, again, I'm only looking at this geographic area. So what I call an extinction of a genus in this area may not be a global extinction event. Although if you look at distributions of living mammalian genera in North America, a lot of them have geographic ranges that are smaller than this area. So many of the observed apparent extinctions are probably true extinctions. Oh yes, so for this to work, it's important obviously to get the body weights, which have to be estimated, and the durations of fossil genera right. I had some concerns about durations of fossil genera, especially for comparing large versus small mammals. I thought there may be some sampling bias. And there are many possible sources of sampling bias, but one thing is that we use very different methods for collecting large mammalian fossils versus small mammalian fossils. To get small mammals efficiently in the fossil record, what we do these days is that we go to these outcrops, we collect bulk sediment sample. So this is a classic grad student doing the hard physical work. And in this case, we just did dry screen washing, but you could use water to expedite this process. Essentially sieving the sediment to collect all these very fragmentary bones. This is up in Washington State. A few years ago I went there. Sadly, we did not find any small mammalian bones by this method. We could just pick up things from the wall of the trench. This is actually from the Pacheco assemblage. And so, in many ways, collecting small mammalian fossils is a lot more labor-intensive than collecting large mammalian fossils. Okay, but how do we actually quantify and compare the sampling probability for large versus small mammals? So one thing we can do is look at the fossil occurrences, in this case, 3 genera through time. Here I've got 3 successive time intervals. We look at genera that are known from at least 3 successive intervals. Well, not all of them, but let's say interval 2 is the interval of interest. We focus on the ones that are known from right before and right after that interval, and ask how many of these genera was sampled in this interval in between. So in this case, the range through sampling probability is 2/3, or about 0.67. And this is the result I got. For much of the Miocene, well, this solid line is showing the sampling probability through time of large mammals, and dashed line is for the small mammals, which are less than 1 kilogram in body weight. For much of the Miocene, well, these dark rectangles are showing the periods when the sampling probability for large mammals was significantly greater than that for small mammals. So if we wanted to compare durations of large versus small mammals, we need to correct for this difference in sampling. Just said that. And I used a method that was developed by Charles Marshall. The idea is, well, we've got fossils from different points in time. The oldest one gives you the first appearance state, and the youngest one gives you the last appearance state. These are observed appearance states. But since the probability of sampling is never 100%, most likely the actual first appearance of this genus was further down there in time, and the last appearance was probably higher up in time. Now, using the range through sampling probabilities that I just calculated, this is the sampling probability curve through time, which I got separately for small versus large mammals. We know how many occurrences are there between the first and last appearance states. Then we can estimate the adjusted first and last appearance states, taking into account fluctuations in sampling probability through time. To be more specific, these median unbiased estimates for the first and last appearance states. So there's 50% probability that the actual last appearance state was younger than this date, 50% probability that it was older than that date. And a lot of grappling with equations and computer codes and sleepless nights went into this process. This may look like something I could have done in one afternoon, but it's actually kind of tedious. And so I got sampling adjusted temporal ranges for 221 genera of North American fossil mammals. And then I estimated their body weights based on publicly available measurements of the lower first molars. And there are a bunch of equations that one can use to predict body weights based on skeletal elements. Body size range we are talking about here is from shrew-sized to rhino-sized animals. I should mention briefly that estimating body weights is a big subject of its own in paleontology. What I've been doing this semester with assistant Lauren Miller, she graduated last year I think, is to come up with a bunch of equations for estimating body size of extinct bunnies. So I've been measuring a bunch of bunny skulls in the collection and see what elements, for example, lower third premolar versus the entire tooth length, which measurements do better in terms of predicting body weights and things like that. Okay, so I got the body weight estimates. And for the phylogenetic regression, I compiled a composite tree from compendia by Christine Janis. This is for extinct genera at a relatively fine scale. And at levels above families, I used Pinin Diamonds et al.'s super tree of mammals. And since we also need branch lengths to do the phylogenetic regression, I adapted molecular clock divergence estimates for some of these nodes. But for many of the finer divergences at the genus level for extinct genera, we really have no idea of when these lineages diverged. So basically, I repeated the regression analysis 1,000 times, each time randomly grabbing a different set of divergent states within the constraint of these molecular clock estimates. Okay, so finally we got to the result. This is the full data set for 221 genera. I also looked at temporal subsets of the full data set because you might say the cause of extinctions may change over time, and that may complicate the relationship between weights and durations. But the bottom line, and well, the way I grouped these temporal subsets is based on the timing of extinction. So these genera in black dots in this panel are the ones that went extinct between 29 and 15 million years ago, 15 and 12 million years ago, and so on. The bottom line here is that there's really no detectable relationship between estimated body weight and durations. And as you can see, there's quite a lot of scattering of data points. So for any given body weight, we have a lot of long-lived genera and short-lived genera. We can also look at this as ecological subsets. So herbivores consisting mostly of gliaries and ungulates. Secondary and higher consumers made up of lipotyphlans and carnivorans and so on. But again, for the most part, there is really no correlation between body size and durations of these animals. The only exception was when I looked at secondary consumers. The carnivoran genera have significantly lower durations compared to lipotyphlans as a whole, but the squared correlation coefficient is pretty low, so we are talking about relatively weak relationship here, and I don't know what to make of this at this point. Lipotyphlans, there's a lot of uncertainty in the estimate for the regression slope. Depending on the particular set of divergence states that was generated, we may or may not get a significant relationship between the two variables. As far as the phylogenetic signal goes, this is Pagels lambda parameter. Lambda of 0 means there's no phylogenetic signal, and 1 corresponds to the amount of phylogenetic signal that's expected from the Brownian motion model. But strictly speaking, this is the phylogenetic signal in the residual error of the regression model, but since there is no correlation between body size and durations, what this is pretty much showing is that there is really not much phylogenetic signal in the durations. And again, the histograms is showing different estimates for different simulations, 1,000 simulations in total. Each one has different sets of simulated divergence states. But regardless of the uncertainty in divergence states, for the most part we get low phylogenetic signal. So these are again, this is the full data set and temporal subsets of the full data set. Also for ecological subsets, in the case of secondary consumers and carnivorans, all of the simulations yielded maximum likelihood estimate of 0 phylogenetic signal. Okay. So the obvious conclusions are, first, there is still phylogenetic structure in the data we have, and I found this to be rather disturbing because if durations have not much phylogenetic structure, it seems to imply that biological traits that are phylogenetically conserved have not much to do with extinction probabilities at the level of genera. I'd like to think that biology has something to do with your probability of extinction, but that may not be true depending on the scale of phylogeny. And as I said, there's not really evidence for scaling of extinction risk with body weight from shrews to rhinos. And the pattern we see is really a lot more complex than what one might expect from simple population biological expectations of low population density and long generation time and things like that. So, a couple key implications of the findings here. Well, I thought there could be different explanation for the observed pattern. So, one, perhaps there's a mismatch across phylogenetic hierarchy. By that, what I mean is, perhaps at the species level, large mammals are at higher risk of extinction than small mammals, but that doesn't translate to the same pattern at the level of genera. And I can only speculate as to how that might be, but if you think about species, well, different species within a genus, it's feasible that even if large mammalian species have high extinction rate, within a genus, an extinction species is replaced by congeners that can compensate for higher extinction probability. Another explanation, which is not exclusive, well, mutually exclusive with the previous one, is that what we know about the late quaternary extinctions from the late Pleistocene to present is really anomalous in light of the Cenozoic history of mammals. Large mammals may have smaller population size than small ones, but in normal times, perhaps population size for large mammals is still large enough such that the difference doesn't really make a whole lot of difference in terms of survival, whereas anthropogenic pressures since the late Pleistocene may have pushed large mammalian populations across some sort of threshold such that these guys are now clearly more threatened. Oh, I think that's it. I'd like to thank these people for the scientific content of this portion of my dissertation research, especially Tony for guidance and his inspirations. But since this is MBC lunch and I don't know if I will be speaking again here, so I thought I would mention a few people in the audience, and I want to thank, that's Eileen, Jen, and Chris for letting me work in the collection anytime, in any way. And also, I believe that's Jim McGuire. He's flipping rocks. And Alan and Rory for letting me join the natural history of vertebrates, which was really fun as well as eye-opening experience for me as a paleontologist. And I could go on with acknowledgements, but in the interest of time, I think I should stop here.
One of your graphs shows
Yes.
a bimodal distribution where all the scattered points are in a group, and then there's another group, and they all show this sort of dumbbell-shaped distribution.
Yes.
And you have enough taxa that you would think that there would be a more uniform distribution across all taxa. Why is there a dumbbell-shaped distribution of body size?
Yeah, well, for one thing, that's in log scale. But at the continental scale in North America, at least there seems to be sort of a, someone called it Bermuda Triangle of body weight spectrum in mammals, where there aren't a lot of species occupying the intermediate body size.
Yeah.
But the body size distribution is really dependent on the geographic scale. So it may not be bimodal if you look at more locally. So.
Okay.
I was just thinking, I don't know if this is true at all, but if there is a bimodal pattern, it might be partially driven by energetics, because most large-bodied mammals are herbivores,
Right.
and the kind of cutoff between, because you have this constraint, is you want to, for herbivore, you want to get larger body size,
right.
to slow down the digestive process so
Yes.
that you can extract whatever comes from poor quality forage. And that cutoff is about the 10-kilogram body mass.
Right.
So you have some evolution driving to large size or to smaller size, so that you could use other kinds of, in small-bodied herbivores, you could use other kinds of things like coprophagy or specialized gut morphology to get nutrients out of poor quality
Right.
forage. So there might be an energetic drive in both body size directions that.
Sure. It may be useful to look at the cluster of small mammals versus large mammals and see if there's any pattern of body size and extinction.
And split out,
Yeah.
in terms of dietary specialization.
Okay, right.
Another question.
Yes.
Could you expand on how you were looking at phylogenetic signal? Because I'm sort of surprised that something like body size wouldn't show strong
the
signal.
body size has strong phylogenetic signal.
Okay.
That phylogenetic signal I was talking about is the signal in the residual after you do the regression. So it has more to do with the durations than the body size.
Okay.
Yeah,
Did you look at the duration individually too? Because
durations individually, if I remember right, they also don't have much of a signal. But like I said, since there is no correlation between body weight and durations, the residual errors you get, well, if you don't see phylogenetic signal there, well, there's not much going on with durations.
but that could explain some of the discrepancy with previous studies, because if they weren't correcting for phylogenetic signal in the body size per se,
Right.
you could get some artificial correlation.
Yes. So previous studies, they didn't always use phylogenetic method. They didn't always adjust for sampling disparity and so on. So
Any other questions?
okay. Well,
Thanks,
thank you.
Susumu, for